Hello everyone. So, welcome to the next week course, the second week of this course. We are starting with the module 1. In the previous week, we have discussed about the definition of minerals and ores and briefly about liberation characteristics. What is the meaning of liberation? Then we have also discussed about the metallurgical efficiency, the concept of grade and recovery. Now, this week we will discuss about the particle characterization. Particle characterization is itself a very vast subject. So, we will focus only on those important aspects of the particles what we must know for optimizing our processes. Now, before we go to the actual characterization part, let me explain you that why it is important to know the particles behavior. If we look at this a technique that in the applied for particle technology, they are mostly related to the particle interaction or and particle fluid interactions. What I try to mean that in any process where we are involving particulate matter of various characteristics, we must understand the what are the different scenarios when the particle hits another particle or when a particle encounters a fluid. And this is a prerequisite knowledge we should have to properly design the processes and to have our the best products. Now, what is that basically the particle property that basically controls these interactions? We said that particle interaction and particle fluid interactions. So, to understand that we must try to understand properly that what are those properties which are essential to evaluate that dictates those interactions. Now, this particle characterization also is not a very easy subject, it presents special challenges that do not exist for the measurement of fluid properties. Why? If you look at the discrete nature of particulate system, it means it is heterogeneous. What does it mean? That is, two particles, if you have collected from the same system, they will not have identical properties. And as we discussed in the previous week, that we are processing in hundreds of tons of material per unit time. So, it is impossible to know the or to determine the individual particle characteristics. So, what do we have to do? Now, we have to collect a representative sample which represents the entire population, and then we have to characterize that representative sample. So, in summary, so sampling is a major issue. Although this week we are not going to discuss sampling, we will deal with this subject sometime later. Now, what is the difference? Why did I say that particle properties are basically very difficult to characterize when we compare with the fluid properties? Fluid properties are basically well tabulated these days. You pick up any fluid mechanics book, you will get to know the fluid properties at different temperature, that what will be their density, what will be its viscosity, and even some of the thermodynamic properties also we can tabulate, we know. But for a particulate system, it is very difficult to quantify like that. Suppose if I give you this example, that if I am giving you 100 grams of sand, can you tell that what is the average chemical composition? Average chemical composition, probably it is possible, but if I say that what is the individual chemical composition, it is time consuming and it is very difficult to do. So, the properties of the system depend not only on the chemical composition, the chemical composition of all these particles, the sand is basically silicates, but it is the particle morphology that also controls the properties of that bulk solids, that is accumulation of all those sand particles. They have a different property, that is as a bulk solid, than the individual particles. The surface area of sand cannot be calculated, it has to be measured. Why? No, the individual sand grains, they may have different shape. I am just giving for example. So, your surface area will change depending on the what is the variation in the shape, we cannot predict it. The properties are not always easy to define even. I just show you the example that where we are even for the very basic elementary properties of particles, still we do not have a general consensus that yes, this is the definition we accept. Simplest examples of this are particle shape and size. I will try to explain more on these two in this lecture. Now, what used to happen that because of this inherent difficulties in measuring the properties, and even earlier days not many instruments were there to measure the different properties of the particles. So, what used to be done by many industries, that they had some rituals, that okay, if these are the mine product coming from this X mine, so their behavior will follow like this type of thumb rule. And we used to, the plant operations used to be optimized based on those guesstimated values. But now, with the availability of the sophisticated instrumentation techniques, even online offline sensors, we can measure the particle properties with much more precisely than we used to have. That is why there is a saying, it is called that do not perform rituals, measure the properties. Now, let me show you that we always when we deal with particle, we always talk about shape and size. Why should we be worried about particle shape as a mineral processor? That is the most fundamental question. Do we really worry? Yes, we do, because particle shape affects flowability. What does it mean? Suppose I have got a container filled up with water. I drop two particles having identical chemical composition, but one is flaky and another one is spherical. Definitely their behavior into the fluid medium, at what rate they will travel through that is called, we call it settling velocity, they will be different. The spherical particle will travel faster than the flaky particle, and that is what is basically affecting the flowability. So, the prior knowledge of particle shape is a must if you are dealing with the flow behavior of a particle and fluid mixture. Second is packing density. What does it mean? Suppose I have got 1 liter volume of a container and I want to pour rice grain. Now, the rice grains, they are inherently they are little bit of flaky type. So, how much of rice grain I can accommodate into a 1 liter container, that will be entirely different than how much of sugar I can accommodate into that. Or if you take lentils, if you take different other grains, and if you compare it with sand. So, it is not only their individual density which is basically affecting, it is also their shape, because that particle shape also affects the volume of individual particles, how much it will be consumed inside that container when they are in a say packing condition, and whether the packing is what type of packing we have, that means how much of void spaces we will have, that will be dictated by what are the shapes of the particles. Then I have already given you the example about the particle fluid interactions. Question comes, how do we measure shape? It is very complicated to define and measure, that you will realize when I take you through the slides. Look at, if I have a spherical particle, all spherical, it has got, what is the uniqueness of this shape? No, it has got perfect symmetry. There is no ambiguity about its size. Size, you can define it as the diameter or maybe in terms of radius also. But when we have non-spherical particles, most of the cases which we encounter, we hardly get spherical particles on the, when we are dealing with the mined products. Each non-spherical particle, they are unique and they require more than one attribute to describe its shape. Only exception is a cube. Like if I have even a cylindrical particle, I need two attributes, that is D and L, which is shown in this figure. But think of this spherical say cylindrical particle. Now, just assume that this is a cylindrical particle, this pane, So, if you drop the pen into a fluid medium, a container having your water, and if you drop it like this, it will have a different travelling velocity to reach the bottom. So, this is the L and this is the D, but if you drop this, it will have different velocity. This thing we will discuss more when we talk about solid fluid interactions in subsequent lectures. So, this D and L, although they are fixed, but whether we should define the shape of this on the basis of your L or D, and then that will depend on where it is being used. Similarly, if we have a rectangle, it has got 3 attributes A, B, C, and even the for a cone it is H and D, that is the height and the diameter. So, we can define them for the regular shape, but even in a dynamic condition when they are moving, that means in a mineral processing plant I said that there are n number of unit operations. So, the particle has to travel along that. So, when they are moving, so that means their orientation also will dictate that what is that attribute of that particular shape is basically affecting my solid fluid interaction or solid solid interactions. If it is of this shape, we call it oblate and prolate, you can define it by A and B, but what about this irregular shaped particle, which we commonly encounter when it is coming from a mined product, because you have blasted the rock or you have mined it through heavy machineries. You do not get even regular geometry. So, we normally get particles having irregular shape, and remember we are talking about millions and billions of particles. Even for an individual particle, how do I define it? What is the shape of this? So, as I have discussed that for regular shaped objects, we need at least 3 aspects, that is size, shape and orientation to quantify it, and for irregular shape we still do not know how to do it. Although, if we look at textbooks, there are various definitions given for defining shape, but what is the most commonly used measures are, that is you first calculate that what is the equal volume sphere diameter of that particle. When we talk about size, we will elaborate more on this. That is, you take the irregularly shaped particle and you displace a fluid. Normally, we do it with water if the particle is sufficiently large, and how much of fluid has been displaced. So, then we can then calculate it back, that if I have a spherical particle of that identical density, what would have been the size equivalent of that particle to have the similar amount of volume which is displaced. So, we can write based on this formula that what is the equivalent volume sphere diameter, that is for size. We will elaborate more on this on my next say the topic. So, shape is basically the concept of defining it has come from the definition of size. So, it is called the sphericity. So, sphericity is defined as the surface area of equal volume sphere. That means, you have got the ds, that is what is the size of my the equal volume sphere that means what is the equal volume sphere diameter ds is equal to 6 V p, that means how much of volume of the fluid you have displaced with that irregular shaped particle divided by pi to the power 1/3, and it is coming from say your the basic calculations of your volume calculation of spherical particles. Now, once I know the ds, so I can calculate that what would be the surface area of equal volume sphere. That means, this particle, what will be the surface area of that, and what is the surface area of my particle whose shape I do not know. So, the question comes, how do I know the surface area? Now, there are surface area measurement instruments available, I am not getting into that now. So, that is one definition which is commonly used while dealing with irregularly shaped particles in mineral processing. Now, I will show you that how do I use this. Like if you look at these particles, and if you basically calculate, and if you look at even under microscope, they are very close to your spherical shape. And so, for a perfect sphere, this value of psi, that is the sphericity, should be 1. So, the more departure from 1 towards the 0, that means it is far from spherical shape, that means it is going towards the flaky nature. So, like that with these images you can see that you are having a high sphericity particles, medium sphericity particles and your low sphericity particles. So, how do I define it? Now, that is based on the sphericity equation. So, for a cube you get a psi value of 0.81, for cylinder it depends on the L by d, that is the orientation. So, if your L by d is 0.5, then it is, and the dimensions of that what is the length and diameter. So, it varies like this. So, smaller the value of psi, greater the deviation from spherical shape. So, orientation is the projected area or diameter of equal area circle, that is another definition. Let us not get into that topic, because it will unnecessarily confuse you. So, I hope that it is clear that what are the challenges even with the defining the particle shape. But the question is that definition acceptable in all the cases? No, because we are assuming that it will behave like an equal volume sphere, it may not. Like the example is that we have got irregularly shaped particles and we want to pour them into a container. So, what will be the packing density? That is not identical with if I have the similar particles having spherical shape. In some cases, yes, you may apply it, but that is how we are basically making compromises even with our say process simulations or process optimization techniques and all this. Now, let us move to the second topic, that is the particle size. This is extremely important property. I would say that this is the single most important property of a particle. Why? Why I am saying that this is particle size is the single most important property of a particle? Because the particle size strongly influences other important particle properties. How? If you look at the particle size, that it controls the balance between the surface forces and body forces. So, when the particle size becomes smaller and smaller, the surface forces they become the dominant forces. Example of surface forces are van der Waals forces, and they are much more dominant than the body forces like your inertia or gravity. So, like your fine particles, suppose I have got 10 micrometers particles, or all the particles are finer than 10 micrometers. So, then what are the particle particle interactions? That will be dictated by the mostly by the cohesive process, because surface forces they dominate body forces, because their individual mass is almost negligible in relation to their surface forces. But if I have 50 millimeter particles, the body forces start dominating. The body forces are much more dominant than your surface forces. That means, their individual mass is so high that they take the dominant role. So, this example validates my statement that your particle size strongly influences other important particle properties. So, friends, we must know that what are the particle size I am going to treat before we decide that how we are going to process it. If we do not know those particle sizes, we are not sure that what are the particle properties I am going to apply to have a separation between your wanted and gangue minerals. If they are very fine, we have to adapt a different technique in relation to while dealing particles having relatively coarser sizes. So, we will continue this talk and the next module also, that how do we define particle size, and there are other issues also. Even when we have a bulk material, it is not the individual particle size what is important, it is what is that entire bulk, how they behave, and what are the basic properties that will be influenced by the variation of the particle sizes. So, in conclusion, I would say that knowledge of the particle size of a system is essential to be a good mineral processing engineer. Thank you very much.